I'm going to show you a fascinating image, the oldest, first, and largest picture of the universe. This is known as fossil radiation. In your lifetime, you'll likely never see anything older, because its light comes from the surface of a massive ball of fire and plasma. From the precise moment when the universe went from opaque to transparent, this primordial light from the early universe does not come from a type of star or some unknown exotic phenomenon. It literally reaches us from everywhere. It bathes the entire sky, no matter which direction we look, and no region of the cosmos is spared from its presence. So much so that Stephen Hawking himself described it as literally the most important discovery of the 20th century, if not of all time, as you can see. Today, we'll try to uncover the mysteries hidden in this strange, speckled image, the universe's oldest and most fantastic picture. The one of the echo of the Big Bang, which contains, as if encoded, information about the size of our universe and how it was structured. And with that, let's return to our primordial light and how we discovered it, or rather, how we anticipated it. Because the existence of the cosmic background radiation was predicted long before we were able to observe it. By the late 1920s, accumulating observations revealed that the universe is expanding on very large scales. More and more researchers are starting to take seriously the possibility that our universe went through a terribly hot and dense state before being cooled by its expansion, a state so dense that light couldn't even travel through it. Hold on a bit, you'll see, it's fascinating. Here it is. We think that, during the first 380,000 years of its existence, the entire universe was plunged into darkness. The matter it contains is in the form of an incandescent and opaque fog, a fog subjected to phenomenal temperatures, where agitation and density are so high that no light can pass through. Because all matter in the universe is in a plasma state, a soup of protons and electrons that can't bond to form atoms or molecules. Because the temperature is then much too high. And this infernal soup is maintained by the powerful rays of light that are trapped inside it. Constantly absorbed and re-emitted by nearby matter, they continually break apart the smallest atoms forming there. As expansion continues and space dilates, the universe keeps cooling. And when its temperature drops below 2,700 degrees Celsius, which is roughly the surface temperature of many stars, the universe suddenly becomes cold enough for what is called recombination to occur. Almost everywhere, at the same time, the electrons and protons that until then had prevented photons, the particles of light, from moving freely, combine and give birth to the very first atoms of the universe, atoms that are almost indifferent to the passage of radiation. The opaque fog then dissipates, and all the light in the world begins to travel freely. In a universe that, after 380,000 years in darkness, suddenly became transparent. And the stage for a sudden burst of radiation that happened almost everywhere at the same time. That's what we think happened. In 1948, some scientists predicted this residual light would reach us from when the universe changed from opaque to transparent. We should theoretically be able to detect it as a faint radio whisper bathing the entire sky. And 16 years later, completely by chance. This radiation is found by two astronomers who, before studying the remnants of a giant star explosion using their radio telescope, try to calibrate it by pointing to a region of the sky without stars to make sure their measurement doesn't contain any unwanted underlying signal. And while they expect to detect nothing, they hear a background noise, a constant static that's always present, no matter which empty regions of the sky they point at. Inevitably, the buzzing is always there, and always the same everywhere. And after weeks spent chasing potential short circuits, checking every single connection, and even scrubbing the pigeon droppings covering their radio telescope, the two astronomers have to accept it. Clearly, this buzzing, impossible to eliminate, doesn't come from interference. It's not their machine that's the problem. And buzzing, it's the universe. They were the first to accidentally discover the light from the origins, predicted by the Big Bang theory, known as the cosmic microwave background. It's also known as cosmic background radiation, or cosmic microwave background. And no matter what name you give it, it takes the form of a faint radio whisper that fills the entire sky, and it can be studied and mapped. Let's clarify that if images of the cosmic microwave background are often shown in an oval shape, it's simply because they're flat projections of radiation coming to us from all directions. In other words, it's a way to flatten the image of a sphere, just like we do with the surface of our planet. The fossil radiation reaches us from every direction. Actually, we can very well represent it like this, as a sphere with our planet at its center. And now, you're probably wondering why, even though this radiation fills all of space, it comes to us from a time in the universe when it was as hot as the surface of a star. Isn't the sky filled day and night with an intense and brilliant white light? Well, logically, we should expect the cosmos to be completely bathed in a powerful and warm light. But, as you may have noticed, that's not the case. This radiation is invisible to the naked eye, and when we measure its temperature, we find that it is freezing cold. And when I say freezing, I mean it. Because it's just 3 degrees Celsius above absolute zero, or minus 270 degrees Celsius that's extremely cold. This ridiculously low temperature might seem surprising when you know that this radiation was emitted precisely at the moment when the universe as a whole had a temperature of nearly 2,700 degrees Celsius. If this fossil radiation reaches us today, it's because it's so cold. It's because after spending 13.8 billion years traveling through an expanding space, it has lost some of its energy and brilliance. It has cooled down, its frequency has stretched, and today it reaches us in the form of tired light. Just to give you an idea, it is estimated that between the emission of the cosmic microwave background and today, the universe has expanded by a factor of 1,000, and the energy of the photons emitted at the end of the cosmic dark ages has been reduced just as much. Because an expanding universe stretches space, and in doing so, it stretches and lengthens the wavelengths of the light traveling through it, gradually lowering its temperature over time. And that's why these intense rays of light reach us today with an energy 1,000 times weaker than what they had when the universe transitioned. It's from opaque to transparent, which by the way is a very good thing for us. Because without that, the temperature of the cosmos today would be almost the same as that of an incandescent light bulb filament. Except that this temperature wouldn't be limited to just the central part of the bulb, but would then apply to the entire universe. If you could magically teleport yourself just after the cosmic background radiation was emitted and ignore the temperature, you would probably be paralyzed and dazzled by an intense white light, like the one coming from the heart of a steel mill, and you would be like a rabbit. Imagine being caught in the headlights of a 38-ton truck speeding away from you in all directions, quickly revealing the universe's intense glow, shifting toward orange, then toward red, before finally leaving the visible spectrum and entering the infrared, and so on, until it finally reaches us today as a faint microwave signal. Despite everything, what if you entered a livable world? Can you imagine the flash's initial intensity? Here's something to imprint its power in your mind. Even though 13.8 billion years have passed since it was emitted, yet the light echo of the Big Bang alone accounts for nearly 96% of all the light currently traveling through the vastness of the universe. In other words, no matter how numerous they are, stars are responsible for only a small 4% of the light, across all wavelengths, that is currently traveling through the cosmos. Okay, now that we've seen why this primordial light faded, we'll try to uncover its secrets and find treasures in it. What first struck us when we closely observed the cosmic microwave background was its uniformity. This is the first photo taken of it in 1962. The strange bar in the center is created by our galactic plane, which distorts some deep skylight as it passes through. But the rest, the entire rest of the sky, is bathed in a background hum, almost perfectly uniform and without any kind of variation in itself. The fact that the measured temperature of this radiation is always the same, no matter which direction of the sky you observe, is not particularly surprising. When you look at the universe on large scales, you find that galaxies and, in general, matter are distributed in an extraordinary way. But at the same time, how can we explain that the cosmos in which matter was originally so evenly distributed ended up producing, over time, galaxies that formed clusters? The answer to these questions came in the following decades, when increasingly sensitive instruments showed that this astonishing uniformity actually hides very, very small disparities. In 1992, the observation satellite Cosmic Background Explorer, whose uncorrected rendering due to the presence of our galaxy you can see here, the Milky Way begins to reveal the presence of a number of spots within the cosmic microwave background. About 10 years later, the Wilkinson Microwave Anisotropy Probe satellite gave us an even more detailed image, showing that, behind the apparent uniformity of temperature, measured at exactly 2.725 Kelvin, there are very slight fluctuations around this average temperature in the cosmic microwave background. Then, launched in 2009, the extreme sensitivity of the Planck satellite allowed us to produce the most detailed map we currently have of the cosmic background radiation, and on which we can see thousands of small spots, all of which originate from temperature disparities in the early universe. What you are looking at is the universe as it was. When the cosmic microwave background was emitted, just 380,000 years old, it was 1,000 times hotter than today. And the entire part that we can see, which we call the observable universe, was then contained in a volume of space millions of times smaller than the one it occupies today. Although no structure had formed there yet, the Planck satellite was able to measure very slight temperature variations from one region to another. And it did so with an absolutely unmatched precision to this day. The maximum temperature differences between the coldest regions, shown in blue, and the hottest regions, shown in red, are less than 1,000th of a degree. Though these thousandths of a degree difference between the hottest and coldest regions may seem trivial, they allow us to understand how matter was distributed and structured on the large scales of the universe. Because these tiny temperature differences observed in this primordial light are the sign of very slight density differences from one region to another, which, over billions of years, will have immense consequences. Thus, the hottest and densest regions will be the first to collapse in on themselves. They will then attract surrounding matter, shaping the universe's cosmic web and eventually forming galaxy clusters. While the colder regions will gradually see their matter attracted by the gravitational force of the nearby, denser regions. And so, over time, they will eventually give way to immense voids in regions of the cosmos, almost completely devoid of matter. Put simply, small differences in density across the universe create lumps. Heavier regions capable of initiating collapses from which the universe will take its structure. And in doing so, the arrangement of these spots that dot the light from the origins is a language to be decoded, and for those who know how, to decipher it. It gives us access to temporal depths and offers us an open window with a view of the state of our primitive universe, just as it was at the moment of recombination. Only 380,000 years after the Big Bang, when no stars, no galaxies, no structures of any kind had yet formed. That's why, today, being able to read the treasures of information hidden in this old, cold, and tired light is one of the major challenges of cosmology. I don't know if you realize how crucial these imperfections are, so I'll say it again for you, but also very much for myself. These lumps, these spots, are glimmers of hope. They are the starting points from which the entire universe took its structure. And if matter had originally been perfectly distributed like this, absolutely everything would have remained homogeneous and boring. Not just for a long time, but forever. Because without these small fluctuations, no star would have ever ignited, no galaxy, no planet would have ever formed, and the universe would have simply continued its expansion in darkness. Luckily, that wasn't true. Studying these clumps arrangement helps us understand how. In the 100 million years after fossil radiation was emitted, matter slowly formed structures in darkness, pulled by gravity. It gathered together, coagulated, until gigantic clouds of gas collapsed and eventually lit up the darkness, and in the process formed clusters of galaxies, which little by little, over billions of years, wove together all the filaments that make up the immense and vast cosmic web of the universe. Being able, with a single image, to reconstruct the precise way matter was able to structure itself, from the very beginning of time up to today, is already quite an achievement. Studying cosmic background radiation maps also helps estimate the universe's size. The irregularities scattered across the surface of this fiery primordial plasma ball. When it evaporated, we deduced the universe's curvature and estimated its size. The topic is so fascinating I'll devote a whole episode to it soon. But remember, the verdict is staggering, and here it is. The universe is far larger than the observable universe, the part we can see, as suggested by space curvature estimates. From the study of cosmic microwave background maps, it has been shown that the entire universe has a radius at least 500 times larger than that of our observable universe. In other words, the volume of the entire universe is at least 125 million times larger than the only part we can see. And that's just a minimum. Maybe it's even bigger, maybe it's infinite. Studying the cosmic microwave background's characteristics has allowed us to estimate its content. Because the distances between the coldest and hottest regions are directly influenced by the proportions of ordinary matter and dark matter, as well as by the amount of dark energy that existed in the universe at that time. Here too, we would need to spend at least 20 minutes on it, so I'll just give you the results of the observations, which match our theories surprisingly well. At the moment when the cosmic background radiation began to travel, there was about 5% ordinary matter, 27% dark matter, and nearly 68% dark energy in the universe. And studying the details of the cosmic microwave background spots has even allowed us to greatly refine the value of the universe's expansion, as well as its age. And all of this in a single image, an image that is still far from having told us everything. Because we also find mysteries and gaps that still escape us, such as the strange anomaly known as the cosmic cold spot, where the intensity of the radio whisper we detect is somehow much quieter than it should be. If this vast, unusually cold region in the southern hemisphere of the cosmic microwave background maps is causing so much excitement, it's because it probably shouldn't exist, since the rates of expansion of the universe shouldn't have been able to give rise to an anomaly of such magnitude. So much so that some people think there's still something here that we're missing. Common sense would suggest that this cold spot, which covers an area of the sky nearly 10 times larger than the full moon. Could a huge unnoticed supervoid exist in this part of the universe? A supervoid that cosmic microwave background radiation passed through before reaching us, slightly altering its energy. But the currently enigmatic nature of this cold spot has led some researchers to develop astonishing theories, such as the one suggesting that this set of spots originated from a collision shortly after the Big Bang between our universe and another, which would be parallel to ours. And so, in a way, it would be a scar, the mark of a bruise. Others even imagine that the cold spot is the residual and almost erased trace of a previous universe, or even the equivalent of an echo coming from the evaporation of a supermassive black hole, also located in another universe. All interesting speculations, but for now, it's impossible for us to test them. Cosmic cross. This cluster of blue spots that deviates from the norm, far beyond what an unlikely statistical chance would allow, is not the only region of the cosmic microwave background that keeps those trying to uncover its secrets up at night. In fact, there are no fewer than 30 other regions that currently defy understanding, and among them, the strangest and most enigmatic is surely, without a doubt, the aptly named Axis of Evil. Cosmologists often create catchy names. Unlike the cosmic cold spot that it encompasses, the Axis of Evil is a region that, as a whole, is very slightly warmer than the average temperature of the background. Cosmic background, and above all, it stretches in an incomprehensible way over nearly half of the observable universe, as you can see in these images, where the contrast has been greatly enhanced. The reason the presence of the Axis of Evil is problematic is that the average temperatures of large regions of the sky should almost perfectly match that of the entire cosmic background radiation, because within it, all the microdisparities should eventually cancel each other out. Given that the cosmic microwave background spots seem to be distributed on large scales in a completely random way. To this already somewhat disconcerting observation, a second oddity is added. The fact that the Axis of Evil is almost perfectly aligned with the plane of our solar system. And so far, no one has been able to explain why. Perhaps it's just bad luck refusing to show itself unless we're missing something. In short, we're still far from uncovering all the secrets of the cosmic microwave background. I have to say, I like the idea that without these small density fluctuations, or little spots, things would be different. For cosmologists, it's a chance to study the universe's origins. Our galaxy, just like the Sun and the Earth, would never have come into being, and neither you nor I would be here. The cosmic microwave background reminds us not to expect complexity to emerge from perfection. Luckily, many imperfections existed from the beginning, and from these tiny density disparities, trillions of galaxies formed, with hundreds of billions of stars around which even more worlds revolve. And on at least one of them, humans developed theoretical models capable of predicting the existence of the cosmic background radiation even before it was discovered. Humans also capable of predicting and discovering the existence of particles and phenomena such as neutrinos and gravitational waves. This could one day let us see even further back in time and obtain an image of the universe older than the cosmic microwave background. Because even if it is impossible for us to rely on grains of light to have an image of the first 380,000 years of existence of our universe, it is theoretically possible to see through what we call the last scattering surface, that is, the region from which it was emitted, the oldest electromagnetic radiation in the universe, and beyond which no more light reaches us. Because the ghostly neutrinos, just like gravitational waves, are able to move freely through the noise. Billions of incandescent and opaque plasmas existed in the early universe before cosmic background radiation could travel through it. Unfortunately, we will have to be patient because for now, we are absolutely unable to develop detectors sensitive to the energy level at which these neutrinos and gravitational waves exist. After being terribly weakened and diluted by 13.8 billion years of space expansion,